Okay, now let us look what will happen if we have a mixture of weak base and weak acid, and still concentrations are high enough, around 10 to the negative 3 or higher. So let's look at a very simple example. Ammonia, ammonia base and ammonium acid giving us H+. So what will be pH if we have separately added ammonium salt and ammonia solution together? Constant that describe this equilibrium is always the same. It's H plus by A. A will be our NH3 and HA will be our ammonium. We can solve this equation for H plus. So Ka, Ha, and A. We know Ka, where we know it from a reference book. We do not know these numbers. So in general case, we need to go and do all calculations for these two separately, and we'll end up actually with cubic equation, and it will be lots of extra work. And lucky, there is very simple approximation, which is at high concentrations, means 10 to the negative 3 and above, equilibrium concentration of base will be concentration of base. So instead of A, I am writing Ca. Instead of Ha, same way I am writing CHA. So this is total, this is total. We know these two numbers and we know Ka, so we directly calculate this number. If we'll take log, we'll have pH equal to pK plus log concentration base above the line, concentration acid below the line, and this is decimal log. This very simple equation, and now let's look what happens to this equation when I change concentrations of one or other components. So what will happen if I'll dilute this solution tenfold? This concentration will drop tenfold, but this concentration will drop by the same factor, this and this. So ratio will stay the same, means acidity will be the same and pH will stay the same. We do something to our solution, but pH doesn't change. Such solutions that have stable parameters are known as buffer solutions. So solution of weak base and weak acid is pH buffer or acidity buffer. Its pH does not change when you vary concentration a little. If you have multi-component system, usually that's one buffer pair, acid and its conjugate base, that determine the pH value of the whole multi-component mixture. For example, pH of our blood plasma is mainly dependent on concentration of hydrogen carbonate and CO2 in our bloodstream. So let's look at example. I have 0.1 molar ammonium salt and 0.1 molar solution of ammonia. So what's pH of this? I have my equation. pH is pKa plus log C base by C acid. From the reference book I'm finding pKa, it's 924. Now C base is 0.1, C acid is 0.1 as well. 0.1 divided by 0.1 is 1, log of 1 is 0. and my pH is simply pK. Actually, I did no calculations at all. It's very important result. If concentration of base and acid are equal, concentration of buffer solution will be simply pKa of our buffer system. No calculations are necessary. Again, all other species in this system, say indicator, any minor admixtures, will follow the pH determined by our main buffer with a high concentration. Whatever I am putting in a mixture of 0.1 ammonium chloride and zero point 0.1 molar ammonia will have pH 924 and will distribute with its own constants. That's very important for enzyme activity in biochemistry. Enzyme activity, so rate of reaction run by enzyme, is sharply depending on pH, usually having a peak in a physiological area. So our bloodstream has pH around 7.4, and enzyme usually has optimum pH around this. If we change pH to the left or to the right, it will stop working. So now, when I have 1-to-1 ratio, my solution, pH is equal to pKa. If I have 10 times more base than acid, my pH will be pKa plus 1. If I have 100 times more base than acid, will be pKa plus 2. In opposite direction, if I have 10 times more acid than base, I'll have pKa minus 1. 100 times acid than base, pKa minus 2. A very convenient table just to see what happens to our system with pH. Now, if my acid has exactly the same amount of A minus and HA, that means pH is equal to pKa. If pH is equal to pKa, ratio A minus to HA is 1-to-1. It goes both ways.